Okay, good morning. So, sorry for writing so much on the board before the start, but I don't have, this is basically everything standard formula about scattering in quantum field theory, and as I said, all of this was reviewed very well by Balt last year in São Paulo. So two comments. So first thing I want to say is like the summary. What did we learn last lecture? So we did this game of complexifying angular momentum in quantum mechanics, and in practice, what did we get from it? Well, we got some way of connecting continuously between bound states and resonances of different spin. So that was, if you want, some structure on the spectrum of the theory that we got by doing this complexification. And then at the end, we also got this more academic limit of the large z behavior of the scattering amplitude, large cosine theta behavior. So in quantum mechanics, that's basically it. That's my understanding of what actually you get from Regge theory. Okay? So today we're going to discuss quantum field theory. And essentially, you get the same two properties. So it will organize the particles of different spin into Regge trajectories. So that's going to be basically the same. And then this academic limit of large cosine theta will actually be describing the high energy scattering in quantum field theory because we have crossing, so large cosine theta corresponds to large energy in the cross channel. I mean, that we will see that in detail. Okay? So in some sense, that's the basic result of Regge theory. So before I go to quantum field theory, I just want to comment on a question that was asked about collision of Regge trajectories. So in quantum mechanics, we saw that Regge trajectories were given by poles of this scattering amplitude, the partial amplitude. And we saw that this came just from solving this differential equation. It was the zeros of this function in the denominator. And this function was analytic as a function of L and K, and the Regge poles were just the zeros. So here I just did a toy example. So I wrote an analytic function and set it to 0, and I found the solutions. Okay? I mean, it's, of course, if you write something which is say a quadratic function of L, and you solve for L, you will find a square root. Okay? So you may decide to call this a collision of Regge trajectories because, well, in the complex K-plane at I and minus I, you'll have these branch points, right? So these have this two-sheeted Riemann surface on top of this K-plane. But I think I would call this just a two-sheeted Regge trajectory. So you would just see that you can actually interpolate what, if you just plot along the real axis, it looks like two trajectories, but when you complexify K, you can actually go from one to the other. And this, I think, is actually quite generic in the space of Regge trajectories. Okay? Okay. That was just a comment on the discussion we had yesterday. So, okay, so let's start here. This I already wrote yesterday. So we will consider scattering of identical scalar neutral particles. So the scattering amplitude will be a function of the Mandelstam invariance, and it will be invariant under permutations of the Mandelstam invariance, so it will be crossing symmetric. We can expand it in partial waves, where z is the cosine of the scattering angle in the center of mass frame. It's just a function of the Mandelstam invariance. And the partial amplitudes can be written in terms of this phase shift. And the main difference with quantum mechanics is that this phase shift no longer has to have modulus 1, because you can have particle production in quantum field theory. And here I just wrote some formula for actual physical cross-sections, if you want to know the total elastic cross-section or the total cross-section. And perhaps the best formula for the comment I made is this inelastic. So if you take the difference, you really see that you only have inelastic, so particle production into some other channel, when the modulus is less than 1. Okay? And so this clearly cannot happen, for example, if the energy is not enough to open the next threshold, like I explained before. And okay, this is just the identity of the orthogonality of Legendre polynomials. If you want to derive these formulas for cross-section starting from there, you can practice that this afternoon if you want to make sure you understand this formula. Okay, any question about that? Okay, so now here I wrote this statement about the analyticity. So let me draw a picture of that. So the statement is that we will assume that the scattering amplitude as a function of the Mendel-Sum invariance is analytic up to some singularities, some poles and some branch cuts, which are basically demanded by unitarity. But in practice, really the best way to understand the analytic structure is just to look at Feynman diagrams, okay? So the conjecture that I want to make is that all singularities of the scattering amplitude, of the non-perturbative scattering amplitude, also appears in Feynman diagrams at some order. Okay? So this is what actually I think Balt called this Landau analyticity, because you can calculate all these singularities from looking at Landau diagrams that tell you the singularities of Feynman diagrams. Okay? So this is not proven in full generality, and so Balt last year reviewed a lot of the partial results that there are where you can prove partial analyticity, but as far as I know, there's no counterexample, and I think it's really a quite reasonable thing to assume about scattering amplitude in quantum field theory. So let me just draw a picture. So let's keep T fixed, and let's draw the S-plane so that we have an idea of what I'm talking about. So what kind of singularities do we expect? Well, we expect a branch point at 4m squared, which corresponds to the two-particle cut, the production of two particles. Then we have crossing symmetry. So let me put it like that. So this will come from, this is S equals 4m squared. And when you fix T, you can also take U equals 4m squared. And so this cut is at minus T. Okay? And all of this you can predict just from looking. So for example, this cut will appear in a Feynman diagram of this type, where you have like a one-loop diagram. You can produce these two particles in the intermediate channel. You get this cut. Here you would have the diagram like that, so you'll get the cut like here. And then you can get poles at positions of stable particles. So for example, let's say there's a particle mi squared, and then this will come, say, from, you will see that even in a tree-level diagram where you exchange a particle of mass mi. And of course, there is the crossed pole from this diagram. And of course, there's many more branch points, which again you can see from Feynman diagram. So if you look at something where you have three-particle production, you'll have more branch points like that. Okay?
S channel is correct.
Yes, sorry. Here I'm saying the S channel. Yeah. S. Yeah.
When you say you mean on the first sheet only?
Yeah, let's say that. I think it's even on the second sheet, we have, I think even on the second sheet, it's reasonable to think that you can understand them from Landau diagrams. But I don't want to be so bold.
Even on the second sheet, in what sense are the resonances determined by, resonance pole determined by unitarity?
No, but that's the spectrum. It's like this is also not, if you have a particle, then you have a pole. But once you have this pole, you know that you will have this cut because I mean, not this cut, but a cut at, if you have a particle here, mi, you will also have a cut here at 4 mi squared, right? where you exchange here the particle mi. So with the resonance, it's the same. If you know there is a resonance, then you'll have cuts where you exchange resonance and particles and two resonances. But the first one is not really, you have to know where the poles are. Yes.
But in what sense is resonance a particle? I mean,
In the sense that it's a pole.
yeah, but how do you know that's determined by unitarity?
Okay, good. So that's perhaps this is not the right word for poles. Of course, poles are not determined by unitarity because I mean I could just say I have a theory without any poles, right? I don't know, pions. No, there's no pole in the scattering amplitude, and there's theories where there are poles. So that's a part where you choose which theory you are. It's which poles you have, right? And then once you know the poles, all the cuts are determined by unitarity. I think that's what I mean by this statement. Maybe it's not very precise.
I mean, I understand the poles on the first sheets are determined by unitarity. I mean, that makes sense. These are actual.
Once you know the spectrum.
Yes.
Right. So I'm extending the notion of spectrum to poles, which to resonances, if you want. Otherwise, you cannot fix them by unitarity. Yes.
So if you make a statement just on the first sheet, you also need to say where the branch cut goes, and the rule is it always goes along the real axis.
I can choose to put it like that, yeah. If I put it like that, then this will be analytic on both sides. Yeah. Any other question?
So for this particular picture, and the consequence of this conjecture are pretty small. You just say that there is nothing, no singularity anywhere else except on the real axis, and that's it.
Yeah, exactly. Yeah, if you then change the masses of the external particles, you can have anomalous thresholds, but those can also be predicted by Feynman diagrams. So that's what I'm trying to say. Okay. So then let's go to complex angular momentum now. So this is just the basic background material. So now let's discuss how to make that angular momentum in the partial waves complex. And the way to do that goes by the name of Frasa-Gribov projection. So the idea, the starting point, we just invert that expansion using the orthogonality of the Legendre polynomials. So here we put t, which is a function of the scattering angle, right? We invert that relation. 1 minus z. Okay. So this I will call t of z, sorry, of z. Once s is fixed, s will be fixed in all the following equations. So this is just t as a function of z. So okay, we have PL. I wrote it yesterday. We know how to continue the Legendre polynomial analytically in L. So you could say that we're done. Okay, that's just analytic in L. Okay, but that's a bad continuation because the Legendre polynomial, if you just analytically continue in L, grows exponentially at large L. Right? We saw that when L goes to infinity, I wrote some formula: cosine pi over 4 minus L plus a half theta. Okay. I think I wrote this formula yesterday. Okay. So it will grow exponentially at large L. So this is not the continuation we want. We're looking for a continuation that doesn't grow exponentially at large L. So the trick to do that is very nice. So the idea is to use the other Legendre function. And this function has the nice property that it has a cut from -1 to 1, or we can, where the discontinuity is the Legendre polynomial. So let me just write that equation. So if you take QL of Z plus I epsilon minus QL of Z minus I epsilon, this is just I pi minus I pi times PL of Z. Okay. So I need some space. Yeah, let's do it here. Let's get that. I lost the big eraser.
It's probably under the table.
Yes. So let's move this. Let's move here, for example. Okay, so what I mean, let me draw the picture. So in the Z complex plane, I was saying that we have this cut from -1 to 1, and the cut of this function Q, the discontinuity is just PL. So I can write another equation where I say that FL of S is just equal to the contour integral around the cut that computes the discontinuity. Okay, so this contour is just going around the cut in this direction. Let's say this is the contour C1, C1. Okay, and as you might expect, now the trick is to open this contour. So we have to know what other poles in this integrand do you have in the complex Z plane. So I'll just write it here. So if you look at the formula for T of Z, when Z now becomes bigger than 1, T will explore its complex space, its complex plane. Okay? And you can think that, I mean, this formula is equally valid for fixed T, for fixed X and moving T, because it's symmetric between S and T, the function. So we will have this kind of analytic structure, where here, let me call this point Z0, is just the beginning of the two-particle cut. So it's 1 plus 2 4m squared over S minus 4m squared. So when T is equal to 4m squared, so it's here the part. When T is equal to 4m squared, I have a branch point. And then I can also have like a Zi, where here it corresponds to stable to poles 1 plus 2mi squared over S minus 4m squared. Okay. And this is symmetric between Z and minus Z, because that's the symmetry exchanging T and U. Okay. So if I put here U, I just put here 1 plus Z. So exchanging Z to minus Z is exchanging T and U. Okay?
Sorry, Joao, is there something between the 2 and the 4? Or?
It's just I don't want to write 8 because it's 2T and T takes the value of 4m squared. You just put a space in Mathematica, right? That's enough.
Yeah.
Yes?
Are you assuming a constant value of S here?
Yes, for the moment, S is bigger than 4m squared, yes. Okay, so as you might expect, we're going to deform the contour, and we're going to pick, open the contour, and we're going to pick these discontinuities. And on top of that, we have, in principle, the contour at infinity. let's call this part C2 and that part C infinity. This part I don't even need. Okay. So let me just write the result then. So the result is there's the part from the cut. So from Z0 to infinity, dz QL of Z. And now you get the imaginary part, because it's the discontinuity of T, S and T of Z. And what do I want to do? I want to write here plus the other cut. So from minus infinity to minus Z0, dz QL of Z. And then I'll just write, I don't write explicitly because I don't need, plus poles plus the integral over the contour at infinity. Okay? And we'll discuss each one of these terms. So first, let's discuss the contour at infinity. So the contour at infinity, so we have to use the property that QL of Z, how does it behave when Z goes to infinity? Well, when Z goes to infinity, it just decays as Z to the L plus 1. Okay, it's a perfectly regular point of the Q function. It's just this pole. It's not. There's no cut that goes to infinity. So if the scattering amplitude is bounded, is polynomially bounded, so if you take S and T, and then this is bounded by T to some power n, okay, but in the complex plane, so when T goes to infinity, then you see this decays as Z to the L, and this T becomes Z because T and Z are just proportional when T is very large. So you conclude that this contribution from C infinity goes to 0 for L greater or equal to than this n, okay, and this power. So we will come back to this power in a moment. No, actually, why don't we discuss this right now? So how much should this n be? Okay. So here one can use the Frazza bound. So the Frazza bound, it's actually, again, it was derived by Bolt if you don't know what it is. But so it's a bound on the total cross section, which tells us that it's asymptotically less than log square of, well, let's say T, okay? Here I'm thinking that T is the large parameter. So using the optical theorem, this gives us a bound on the imaginary part of T at S equals 0 and any T must be less than T log square of T. Okay? But in fact, I mean, this is, if the total cross section cannot grow like that, then the differential cross section can also, I mean, it must be even smaller, right? So in fact, if you put S, if you put here S negative, okay, which corresponds to the scattering in the T channel, physical scattering in the T channel, then we know that this must also be bounded by that. Okay? So in fact, this tells us that n should be 2. Okay? Should be enough to bound by a quadratic polynomial, because this is just linear plus some log. And so the contour at infinity we can drop it as long as the spin is 2 or higher. Okay?
If we assume that x was positive, now you are
Good. Yeah, then here it was a bit of it was a bit fast. So here it requires a few more words. So what is the idea? Let's do the argument in this order. So we first don't know the n, but there is some n. Okay, there is some n, and we calculate, and L. We take L bigger than. No, sorry. What I want to say is the following. This expression, once you are here, now you can analytically continue in S. And you know the analyticity in S. Okay, that's one of the analyticity conjectures I'm saying, that it's analytic in S. So as long as you can move to a region in S where this function does not grow, okay, where this function, and here you can move to negative S, and it's bounded. So for negative S, you can compute for L less than 2. And then, well, once you get the function for some range of S, since it's analytic, you get the function for all S. For L greater than 2. Yeah, sorry. But in fact, it's actually.
You don't get anything because maybe that function is analytic for S negative, but then it has region of analyticity has some boundary.
In S. Well, but that's precisely one of the. That's why I wrote this conjecture about the analyticity in S. Okay. So in fact, you can even go further. If your scattering amplitude has some value of S, some region, this is really a very bad upper bound, right? Very safe. In general, you can find a scattering amplitude where this actually decays, goes to 0 as t goes to infinity. If you take S sufficiently negative and fixed, you can find, in many experimental scattering amplitude, that's what happens, okay? And so in that case, you can even go all the way to L equals 0. Okay?
Sorry, can you write this bound? You're assuming t is real and positive.
Sorry?
You're assuming t is real and positive in writing this bound.
No, no, we know. I think we we know that it's bounded everywhere in the. If you fix S and you just go to t in the complex plane, it's bounded by t squared. Yeah, that's.
But the argument for Poisson bound, I thought it was in the for the physical cross section. But now you are extending that statement to arbitrary complex t.
Yes, I think the statement is that if you bound the cross section, then you cannot grow faster in another direction in the complex plane. Yeah, I think that statement is true.
Because technically the assumption is that it's polynomially bounded at infinity.
Right.
In any direction.
And once it's polynomially bounded, then
Then you derive the Poisson bound physical t, and then you write the dispersion relation, where you know by assumption that you're only finite linear subtraction. And then
right. Right.
You can find that
Right, exactly.
bound holds everywhere in complex. Because you know the number of subtractions is not completely.
Right. Yeah, so what Balt is explaining is that once you know that it's bounded for real t, so you know how the imaginary part grows, and you also assume that it's polynomially bounded, so you can write a dispersion relation, and well, you know the dispersion relation, you just see explicitly the dependent on t, because you just have an integral over the imaginary part, and the way it grows at infinity is just the number of subtractions you need. So if you have this bound, you only need 2 subtractions at most. So
somewhere there's a slight stronger assumption it's polynomially bounded to begin with.
Yes, so that's what I'm saying here. But once you assume that there is an n, then you can show that it must be, that 2 is sufficient. Yeah.
And how do you argue this polynomial bounded to begin with?
That, no, that is kind of an axiom. In some sense, it's like a consequence of causality, but yeah, you see, causality, well, this goes into a bit of a dangerous discussion, but tells you that when you have this signal propagation, right, to not have a causal propagation, you must be able to close the contour. Well, I'm not explaining this property, but you know what I'm saying? That you, in the energy plane, you need to be able to close the contour. So it tells you that it must be analytic, and also it cannot grow exponentially, because otherwise you cannot close the contour. I mean, sorry, let me continue, because if I go into this, we'll not move to any real equations.
Can I ask you another question about your configuration from positive S to negative S? Do you have to worry about singularities of the integrand crossing the contour of integration when you continue S?
Right, you have to be careful when this pole will move when you continue in S. Sorry, this branch point will move, so you have to be careful. If you come here, you either come up or come down, and that gives you a branch point in the S plane, right? When this branch, you have to decide which side you go. That's how you get the branch points in the S plane of the partial amplitude.
So I'm just saying that that formula you wrote
Yes.
may not literally apply to negative S because of the animation. You pick up some additional contributions.
No, again, since this formula is true for positive S, and you have analyticity in S, you just continue in S, and you just see what happens to this integral. Okay, if I have this integral around this cut, if this branch point moves here, I mean, I just have to continue. I just do analytic continuation of the integral. That's what.
But the result of that continuation, the right-hand side, that you may have to change the contour or something like that. The Z integral on the right-hand side of the formula.
Here.
Yeah.
But it's like by definition, once you have this contour, the analytic continuation is just what you have to do is you just see how the contours move with each other, right? That's the analytic continuation. There's no freedom. You cannot just do anything discontinuous on the contour.
Sure, but I'm just saying that the result of analytic continuation, you may not be able to evaluate the same function by literally computing the integral along the same contour.
I mean, of course, if this point goes here and then comes down here, it's complicated, right? You have to do that and continue the Legendre function inside the cut to do everything analytic. Is that what you mean? That the contour will look different?
Bound on the integrand, you may not be able to literally plug that bound into the integral because once you have continued to negative S, you might have to pick out some extra contribution from the singularities that cross the contour of integration.
Can we discuss that idea then? Yeah. Okay, so that was about the contour at infinity. Let's see if this part is less controversial now. So here, I'm just going to use a simple property of reflecting in Z. So, of course, this is equal, not of course, but this is equal to QL of minus Z minus 1 to the L for integer L. Okay, so at the moment, I'm still doing this at integer L. And here, I can, as I said, I can just put a minus sign because that's just the symmetry, UT symmetry of the imaginary part. So now I can just change the integration variable from Z to minus Z, and I get exactly the same, and I just left with this factor minus 1 to the L. Okay, so the final formula, I'll just write the final formula. Yeah, I have to write it like that, yes. 1 plus minus 1 to the L. So this is the same thing, S and T of Z plus poles. And so the point here that I want to emphasize is that this is one difference between quantum mechanics and quantum field theory, is that you have to analytically continue separately the even and the odd spin. Otherwise, this factor will grow exponentially at large L. Okay? So for L odd, well, in this simple case, because all particles are identical, you just have L of S. The continuation is just 0 everywhere because everyone is 0. Okay, but in general, you will have non-trivial. And the continuation for the even, you just put there a 2. And I'm just going to write it by changing integration variable. So from z to t, so this is dt, and there is this measure 2s minus 4m squared, ql of 1 plus 2t over s minus 4m squared, imaginary part of t of s and t. And okay, I won't write the poles explicitly, just not to waste more time, but the poles is immediately, you can just get it from here. You just put the imaginary part equals some delta function, and so you don't have to do a calculation independently. It's just the same, right? The imaginary part, if you have a pole in T, the imaginary part will be delta function times the residue, or pi times delta function. Yes. Q, that's actually useful. That's what I'm going to say now. So QL of Z, well, there's some proportionality factors, but then you can write it as a 2f1 L plus 1 over 2. Okay, so it's symmetric Z to minus Z, and it has the branch points at 1 and minus 1. So at Z equal 1 minus 1. And actually, this is useful because when L goes to infinity, so now if you want to know what's the behavior of this continuation, okay, so now this is equal, for every integer is equal to our partial amplitudes, but what happens when L is large and complex? So that we need to know the behavior of this function. Sorry, this is exponential. Thank you very much. That's important indeed. Otherwise, it would not go like 1 over Z to the L plus 1, like I said. Yeah. Z. Okay, so if Z is bigger than 1, then it decays exponentially at large L. And so you see here that you see here that T is positive, and if you take S bigger than 4m squared, then this decays exponentially at large L. Okay. So FL. So the conclusion is that FL plus, so this continuation goes to 0 as L goes to infinity. Any question?
Is this limit uniform in Z?
What do you mean? Sorry, what do you mean by that?
Well, you send L to infinity, but do you need to take into account?
Z is
Do
fixed.
you need to assume anything about Z, that Z is, say, less more than 1 or?
Yeah, sorry, I should have written that. Yeah, Z, sorry. Yeah, Z is more than 1. Yeah, Z here is bigger than 1, yeah. Sorry. So this is when this log is positive.
Yeah. What would have gone wrong if I just used the first formula with the PL?
It will grow.
But I can still do the
So
one integral.
So if you have a function that you know its values at the integers, there's many continuations to the complex parameter, right? So you will get another one, but that one would not be good, for example, to do the Sommerfeld-Watson transform because it will grow at large L and you cannot drop the contour at infinity. Okay, so
Sorry, so you're now still assuming S to be bigger than 4m squared in that statement that f of L goes to 0?
yes.
But did you use the first order bound? I mean, don't you want to say S is less than 0 in that case? I mean, how did you find this?
Let's do the following. Forget this part. Okay, there is some n. Okay, let's just assume polynomially boundness, and then everything is good for L bigger than that n. Okay, then we can debate what that n should be. Can we separate?
Yeah, but in the Z formula, 1 plus 2t over s minus 4m squared, the integral runs from dt being 4m squared.
Yeah. So
So s is negative in the physical.
no, S here, S is bigger than 4m squared. To get that decay. Okay. I'll write it here, okay? S bigger than 4m squared. And L bigger than this n, okay? Then we can debate this n, and I think the Frazza bound, but that's a much more subtle issue because you have to continue in S and then make the argument, okay? Okay, so Regge pools, so they are just pools of these partial amplitudes. So the idea is that you can have this partial amplitude, and now is an analytic function of L, so it can have pools in L, and I'll use this same notation of n of S. But of course, you can also think of this is also a function of S. So you can also think of this same pole as a function of S, and you would write it as S minus some mass square that depends on L. Right? So that's just thinking of it as a pole in L or thinking of it as a pole in S. It's analytic on both. So you see from here, you see that you get the spectrum of, poles in S for integer L are just the spectrum of the theory. If this is real, it's just a stable particle. If it's a complex number, then it's a resonance. Okay, so that's exactly what expected. And so I just want to draw this picture because that gives you another property, which is factorization of the residue. So if you think like that, we know from, well, from unitarity, from factorization, that if you exchange here a particle of mass mn, then let's say this is a process 1, 2, 3, 4, then the residue here will be some coupling 1, 2. Well, that in general can depend on L, on the type of particle, and 3, 4, right? The residue will factorize. If I change this particle and I keep that, I keep part of the residue. Okay? That comes from unitarity, factorization of the residues. And so the same property is true here. If you think in terms of L, you also have residues which factorize. So I can think of it like that. And that I'm just writing that because that has experimental consequences. You can look at different scattering processes where you just change one side and the other, and then you compute the high energy behavior, and that must match because of this factorization of residues. I'll explain that better.
I'm sorry to interrupt you here, but so you are assuming that S is fixed and real, or you also allow complex S to see this proof? How do you analytically continue FL of S for complex L and complex S?
Okay, so let's start again. So we are here. Everybody agrees with that. Here I take L integer and S bigger than 4m squared and real. Okay, I'm very safe. Then I go here, and I have to worry about this contour at infinity. Okay, so the contour at infinity, I need the function for fixed. Let me see, fixed S and positive, and large T, right? And I use polynomial boundness, okay?
I
So,
don't question your logic anymore. I just want to see an equation which accomplishes.
no.
You have an equation which accomplishes this analytic continuation.
I'm getting there. So in this region, okay, I can get to this equation, and now in this equation, I can take L to be a complex parameter, okay, and this decays at large L, okay. So now I'm done. Now this is my function. It's an analytic function of L, and it's also an analytic function of S. It is. I calculated it for S real and positive, bigger than 4m squared, and here it is. But now it's an analytic function of S. I can take, because this is an analytic function of S, but the imaginary part is also analytic. I mean, it's just a difference of
Imaginary part is a difference of analytic and anti-analytic functions, not analytic in S.
it's the function on top of the cut minus the function on the bottom of the cut. And moreover, this imaginary part is on the T cut, right? Okay. So S is not being complexified in this imaginary part. It's T plus IS or minus T. And then I can just move S and see what happens to this definition of the function.
Okay, this was what I was missing.
Okay, good.
And what do you follow up on Slav's question? What do you expect of the analyticity on the S plane now for complex L? Do you expect the same kind of branch cut and close structure?
Yeah, that's a very good question. So yeah, in Gribov's book, there's a nice discussion about that. So if you now, so as I said, you'll have branch points from when now you move this integral, right? This will touch these other branch points, and we'll have branch points. And so in the S plane, you will have this branch point at 4m squared, where you started here. And then you also have a branch point at 0. Okay, it's the right cut and the left cut. And yeah, you can show that even for integer L, it's just like that. And then when you complexify L, you could worry that as L moves continuously, you could get like singularities coming out of these cuts. And so Gribov shows that actually from this one you cannot get anything because you can calculate the discontinuity and you see that it's always finite even when you move L complex. And from here, it's a bit more subtle. From the elastic cut, right, there are several cuts here. So from this elastic cut, the only thing that can come out is poles. You can also show that from unitarity. But from the inelastic cuts, you could, in principle, for complex L, get something more complicated. It's an open question. It's not known. You could get some cut coming out in between the integers.
The Regge resonance poles, are they on the first sheet or are they on the second sheet?
No, if they are, the resonances are on the second sheet. Yeah, of course. Yeah, you cannot have poles here.
Even for complex L?
No, sorry. For integer L. So again, so let's do this. I did this last time. So for example, you could have for L equals 0, you could have some pole here, which is some particle, and then it moves. I think you won't have a break, but it's okay. I had a big breakfast. For L equals 2, you go there, and then you can enter the cut here, and I mean, some trajectory like that, and say for L equals 4, you have a resonance here. Okay? So if you ask me, do I have to... Yeah, I think you have to enter the cut like that. So for whenever you are on the first sheet, I think the pole must be exactly on the real axis, yeah. For real L. If you complexify L, of course, this curve will change. So yeah, doesn't really matter. Depends how you move between two integers. It's a big crisis. Okay, so let me try to shortcut this then. This I already said. So the conjecture that one can make, if you want to be bold, is that all particles belong to Regge trajectories. So that's sometimes called nuclear democracy. Okay? So if I could convince you about this Froissart-bound argument, then this would be true for L greater or equal to 2. Okay? So all particles and resonances with spin 2 or higher, then we already know that they indeed belong to a Regge trajectory. It's not entirely obvious. It doesn't follow from what I said that it's true for all spins, including 0 and 1. But as I emphasized here, if there is some value of S for which this the imaginary part actually goes to 0, then you can just compute that there, and then analytically continue from there. Okay, so I think it's actually a reasonable. It's not. I don't think it's a conjecture that is ruled out that all particles actually belong to Regge trajectories. Okay. Okay, and I think I have to give you less details about the high energy scattering technique. I already discussed this with, it's just a Sommerfeld-Watson transform. The only difference is that now we have even and odd spins to continue separately, but that's just a small technicality. So this is.
Sorry, about your earlier comment. When you say all particles belong to the Regge trajectory, what do you mean by particle?
Poles in the scattering amplitude.
All poles.
Yeah. Yeah, the question is if there are poles, that there are partial waves. yeah, suppose you take this function and you analytic continue in L to L equals 0. Will you actually get the full exact scattering amplitude partial at L equals 0, or you will be missing some piece because the continuation does not work at L equals 0? There's some kind of delta L of 0. That's the non-trivial question for this conjecture. Okay, so you just take, so now, well, okay, the starting point is the partial wave expansion, but in the T channel, so I'll interchange, what do I mean by, so this is now cosine theta T, so scattering out in the T channel, I'll still call it Z, and it's 1 plus 2s over T minus 4m squared. Okay, and the question is, what happens to this when S goes to infinity, so at high energies, what happens to the scattering amplitude? So, okay, from here you see exactly the same problem. This just goes like S to the L, so we are outside the convergence region of this sum, and it looks hopeless to get it from there. So the trick is again to do the Sommerfeld-Watson transform. So we just change the sum into an integral, and I put here the continuation that we found before, and then I only want this term to contribute in the even, so I put a 0 in the odd integers, and in principle there would be a contribution with FL minus of T, where I would put PL of minus Z minus PL of Z, where I would have a 0 in the even integers, okay? But in our case, this is 0. So I don't care about the second line. So you have these poles at the even integers. You have this contour C. And again, what we're going to do is to deform it to this region close to minus a half, plus possible contributions from poles. Sorry. And here we really don't know. We could have cuts. We don't really know what is the exact analytic structure. Right? So this part is Dragonland. Okay? We don't know what's here for negative L. So, but the idea is that if you call this, so let's say this pole is some Regge pole alpha of T, if you assume that the singularity with the largest real part is a Regge pole, then you can just pick the contribution from that Regge pole, and then you just use the fact that the Legendre polynomial grows like a power, the continuation. And so I will just write here the final result because the argument is exactly the same. So we'll get a residue at L equals alpha of T of this FL plus of T times S to the alpha of T, right? So that's the Regge behavior, is this power law behavior where the power is fixed by the spin of the leading Regge trajectory. And this spin, this effective spin alpha of T, depends on T, on the momentum transfer, okay? So that's the, assuming the leading singularity is a pole, then this is the simplest high energy behavior that you expect from Regge theorem.
Why was L equals minus half special here
It's just because it's the symmetric, it's when these Legendre polynomials decay. They go like 1 over square root z when z becomes very large. Okay, it's they have this reflection symmetry around. So if you go further, they start to grow again. So it's better to stop there. Okay, so let's discuss a bit of physics. Here, why not? Oh, let's keep this one. Let's erase the most controversial board.
This process bound by quality for alpha of t.
Can you repeat this?
Does the process bound, the thing that you just erased, imply an inequality on alpha of t on the leading projectile?
Yes. That's what I'm going to explain now. Thank you. So now if you know the high energy behavior, you can calculate, for example, the total cross section. So that basically at large energy just go like the imaginary part of t, s, and t equals 0. So if you replace that high energy behavior, you see that it goes like s to the alpha of 0 minus 1. Okay? So Frazza bound implies that alpha of 0 must be less or equal to 1. Otherwise, it will grow faster. And if you want to actually get the Regge trajectory in more detail, so you can look at the elastic cross-section, a differential cross-section. So this is also 1 over s, but times t. And so this will go like s to the 2 alpha of t minus 1. Okay? So you can try to read that from experimental data. And it's useful to think of, to expand in t around 0. So you can write this as alpha of 0 plus alpha prime times t plus order t squared. Okay? And if you don't explore a very large range in t, so this linear approximation to the trajectory is important. And this is the slope, which survives through string theory until today, alpha prime. And this is the intercept, the Regge slope and the Regge intercept. Okay, and now I want to discuss some physics, some real-world physics. And I guess I won't have time for conformal Regge theory, but it's okay.
Can you get one more lecture?
I can continue a bit if you want during the break. We do that. I stop for 2 minutes. Whoever wants to leave, leaves. And I do the conformal Regge theory during the break for the ones that are really interested. Okay, so is this any useful? Does it have any realization in the real world? So let's see. So let's plot a few particles. So let's plot here the mass of the particles versus the spin for some mesons with isospin 1, so vector mesons. And so we have here spin 1, 2, 3, 4, 1, 2, 3, 4. And then you have here the row meson. And sorry, let me do this better, something like that. And then there is like some mesons which lie almost in a straight line. So this is just, there's some names. A4, I guess, nowadays. Okay, and just for reference, so that you have an idea, this is like 1 GeV square. Okay. So this plot, it's called the Chu-Frautschi plot, And in fact, we have the great privilege of having Professor Frautschu here with us. So I hope you will correct me if I say something wrong. So that's already a good indication. You see that there is some particles that align in some natural curve, which in this case is really just a straight line. So this approximation works very well. But there is more than that, because you can also look at scattering, high energy scattering, say, maybe I'll draw it here, of pions with protons. And so if you look at this process, pion proton goes to pi 0 neutron, you can exchange here the rho and all these particles of the right quantum numbers to be exchanged here. And so you expect that this high energy process is dominated by this trajectory. Okay? So in fact, you can like fit. You take the log of this differential cross section, this sigma d omega for this process, and you fit to 2 alpha prime effective of t minus 1 times log s plus some function of t. Okay, and then you plot here. Also in this axis, you plot alpha prime effective that you get for every t as a function of t. So t is negative in the real scattering, so you get some points here. I don't know, some error bars. Okay, so you see that indeed, as exactly as predicted by Regge theory, if these particles belong to a Regge trajectory, the continuation of the Regge trajectory for negative t will control the high energy scattering. Okay? So this is really, if you want, the most important success of Regge theory is to at least partially explain this experimental data. Of course, it's not really explained because it doesn't predict the trajectory or why it's linear, but it makes sense of this connection between the spectrum and the high energy behavior.
Joao?
Yes?
Since the Rho-Meson belongs to this trajectory, does this imply that Q-speed has nicer behavior and energies than the first half-bound? The N is repeated?
Yeah, so you see, this is here it's one case where you can go to this region. So here the alpha effective is negative, right? So actually the cross section decreases at high energies. So that means you can actually analytically continue for all L all the way to 0. So then it's natural that all particles really Regge-ize. It's just consistency with that.
In practice, the data here doesn't really go much below L equals 0 in a clean way.
So you say it only goes, it's basically this region that is explored.
Enough other complications enter that you can't see the continuation cleanly.
All the way down here. Okay, maybe my scale is a bit exaggerated. maybe here I should put something like that or something. Thank you. Okay, so yeah, I have another comment about experiments. Well, this factorization that probably I erased, it's also, you can also check it experimentally because it gives you relations between different processes at high energies, which are to some extent verified. So I'll skip that. But I just want to tell you some words about a specific Regge trajectory, which is called the Pomeron. So the Pomeron is a Regge trajectory with the quantum numbers of the vacuum. So it's neutral and parity plus and all that. And so it's a Regge trajectory that is exchanged in every elastic process. So for example, if you, it's the Regge trajectory that dominates total cross-section. So for example, take proton-proton to anything, the total cross-section, yeah, let me just give you the plot. I think it's better. So let's do like that. It's the same type of plot. So here I'll put T, and I'll give you here the scattering data. I say 2, 4, 6, and so this is 1. And the scattering data of this alpha effective, which you can calculate as a function of T, passes, so it's on the negative side, and it passes very close to 1. Well, I don't remember if this goes well below or not. This I don't remember. But it's actually a very slight trajectory, so alpha effective of T from experimental fits is found to be like 1.08. That's the intercept, plus 0.25 T in GV units. Okay, so that's for proton-proton. This is from PP to PP, right? From the elastic cross-section, you read off this alpha effective. And for a long time, it was a bit unclear what was this trajectory, because it's hard to find the particles on this side. But actually, I think now the best results you have is from lattice. So from lattice, just pure glue SU3, pure glue, you can calculate some glue ball spectrum. And let me just plot it here. So this really works pretty well. So there's like, here there's some bigger, but this is Meyer and Tepper in 2004. And they get a fit where alpha 0 is of order 0.9, okay? So it's not exactly 1, but you kind of see that it's the same type of trajectory, okay? So this is still, this is the picture of high energy scattering in QCD, is that the particle that dominates total cross sections is this Pomeron, and the intercept is very close to 1. In principle, it should not be bigger than 1 because of the Frazza bound, but experimentally, we still see the cross sections growing, and we can fit very well with the power to that.
You said that quantum numbers of the vacuum.
Yeah, except the spin, of course. Spin.
But PP has charge too.
No, but it's exchanged. It's what's exchanged, like PP, what's being exchanged here. PP goes to PP, or okay. So here in the elastic is what you exchange like that.
Why should we expect these to match since pure glue is a different theory?
Right, that's a very good question. So the idea is that the Pomeron is mostly a gluon trajectory, a glue ball trajectory. So the effect of having the quarks will change the masses slightly, but it's a small effect. That's the idea on this trajectory, because it's a mostly gluonic trajectory instead of a mesonic trajectory like here. Yeah. Also, the n counting also works. If you do large n, this is like a closed string. It's not an open string like a meson. Yeah.
But then why do we not see this? If that's a small effect, then we should see these particles in the real world, and we don't see any resonances. So they have a huge width in the real world. So they presumably in the real world they sit somewhere in the complex plane. That's why we don't see them.
Right, but even in here, these particles are also resonances, right? They're not, I'm plotting, I guess I should say that I'm plotting the real part of the mass, because, I mean, in SU3, this glue ball will have a mass above twice the lightest glue ball. So this will also be a resonance. Okay, so that's a good question. I don't know what is the width they measure on the lattice, but yeah, this is also a resonance. Okay, it's time for my 2-minute break. Okay, then, but since I'm going to stop here, let me write this equation. So from the Pomeron fits, you get something like that. S in GeV units. So it's so rare that I can write this kind of experimental data that let me just finish with that. Times 27 millibarn. Okay, that fit works very well all the way to LHC energies. Gives you the total cross section in proton-proton scattering. Okay, proton-proton to anything. So you should compare that with the Frazza bound. Okay, the Frazza bound, it tells you it should go like log square S, and okay, here we don't know exactly what is the coefficient inside the log, but should be something characteristic of the theory. It doesn't matter much, doesn't change much. So let's say GeV, but then here the coefficient it's 70 millibarn, which comes just from pi over the mass of the pion square. Okay, that's the coefficient that you get in Frazza bound. And if you work at energies of the LHC, this is still way off. Okay, so there's really no real tension in terms of numbers between. It's more of an academic question of what is the actual asymptotic behavior. Is it going to be like that, or is it going to be like a constant, or is it going to be just like a log? Okay, this we know that it cannot be. It cannot grow because at some point, but the energies at which this becomes bigger than that are really way, way, way off experimentally.
So there's not a big factor then. The difference between these two numbers.
Yeah.
No, I think there's a much bigger difference.
No, if you calculate, the point is that this grows very slowly. Sorry, this also grows very slowly. So this at the LHC is like 15, if I calculate correctly, and this is like 4. So it's a big difference because this is really rising extremely slowly. So if you calculate the S at which they become the same, I forgot to copy, but it's like really, I don't know, Planck scale or beyond.
The difference was even larger.
Okay, I think I got the numbers right, but yeah. Okay, so I have like a quick summary of conformal Regge theory. I will do it in 5 minutes. Thank you very much.